that the two morphisms in all generality will be not in H but in G cross H, so in the direct product of G and H. I've not made a list of the properties here which you can recheck as exercises, but you can also find proven in or shown in diagrammatic form in my notes. So the fact that T is a group homomorphism between H and G. This here is important. It's yellow because we'll keep it in mind for later. Is how G actually acts on H. Then we have again here two properties of these two are properties of the alpha action. It's basically the fact that alpha actually defines an action of G on H because it's a map to the automorphisms and it's a homomorphism as well, as you can see here. And here in red is something you can try to do as an exercise, see how so we said that general two morphism, is two morphism is in G cross H. So there in the exercise you can try to make G H act after G prime H prime, and you can do this with both the horizontal and the vertical product in here, and you can convince yourselves of these properties. And you can see that actually it's even more, the general two morphisms are actually in the semi-direct product of G and H, under with this action alpha and this horizontal composition from here. That's nice. I mean, if you draw it up in a diagram, it's very easy to see, and it's a nice exercise to get familiar with these things. So of course we had said in the normal gauge theory that the functor from the space-time manifold interpreted as a category with these homotopy classes of paths and so on was basically enough to define as a one-form connection. Now here I built up all this stuff to convince you that you can do the same, basically play the same game with the to discover what two connections are and how they behave. So we're going to try to see. We have to now make a two functor. Now you remember I told you the rules last time, I think, of the two functors as well. So again, it's the same as before. They map objects to objects, morphisms to morphisms, two morphisms to morphisms, preserving everything there is, which here is horizontal and vertical composition, and all the identities. So the question is, sorry, I forgot something, of course. This is also good to know. So there's one more rule for the two group, which you can check easily, and it's if you ask yourself, for example, what does one H do to another H? Like if we make, our two of these starting at identity morphisms, how do they act? So this is the diagram you would start with. So you have, let's say, a H prime here in the middle, which is the main one, and we're wedging it now. You remember, to get the action of G, we wedge it between G and G minus 1 up here as morphisms, and now we're going to wedge it between H and H minus 1 inside as two morphisms, and with a little bit of manipulation and inserting of some identities, you can find out that basically this is the way. If you horizontally compose H with H prime and H minus 1, then you're getting basically the action of what H gets mapped to on H prime, which maybe has to be expected, but okay. Because anyway, it's a semi-direct product structure, so okay. But in the diagram you can basically read it off. And furthermore, since we have been talking now always about Lie groups, G and H are Lie groups, so they have all their nice manifold properties. So this can be, being Lie groups, the thing can be differentiated to some sort of a Lie algebra. But okay, here we start with a two group. What's going to come out here is we'll call it a strictly two algebra. And this is also, as the cross module was known in mathematics, this is known as the differential cross module, for obvious reasons. But to us, it's known as a strictly two algebra. And these are all the ingredients differentiated from before. So we have G, H, T, and alpha. Now we have little g, little h, and underline the differentials of these maps of T and the action alpha. Of course, obviously, G is the Lie group of the Lie algebra of G, and H of H. And the two rules we want to keep in mind that define the structure of this thing are these two in yellow. So one is the above mentioned Pfeiffer rule rewritten, and the other one is the action, in some sense, the action of G on the action of the stuff in G on the stuff in H. And here I'm using, you see these square parentheses, with these I mean the Lie brackets of the algebra G and H respectively, right? Because here we have two Lie brackets on G and H that are well defined because we're talking about Lie algebras. So far so good. I emphasize these things, as you can imagine, because those are the things that later we will have to give up. But in the meantime, this is what we have, and now we're wondering about this two functor that will give us our two connection that we've been chasing after. And here the sloppy handwriting will begin. So as we have doubled the group, we will also, you can imagine, we also have to double the structure. Now, it's clear, we said the two morphisms are in the direct product of G and H, so it's not like we can, just because we're looking for two forms like B, that are two forms, sorry, this symbol is badly written, but it's a big omega, you know, two forms on M valued in H, I mean. And we cannot just take B and forget about A and say, you know, we'll just use a two form now because we're spanning areas, because these H's, they only go from the identity to something. If we want to have the generic two-morphism, or the generic way to surface between one path and another, we have to include the information about the path, which is still encoded in that same old functor from before that associates A's to paths. So connection one forms to paths. So, of course, so now, okay, so now we have a one form, we now have a one form and a two form, one valued in G and one valued in H, and we will have this, our usual, our two functor, which will again map x's points on the manifold. So this is the manifold, let's say, and here is our two group, GH, let's call it. So x's will still get mapped to G. So points on the manifold will still get mapped to the one object on the group side. And now we have still our classes of paths. They still do the same. They go to the functor of the path, which will still be that nice, well-known holonomy functor. And now we have our two morphisms, which are now these classes of surfaces, which I call sigma, and they will have to map to some sort of f of sigma. And of course, our best guess is to say, why not write it as something with some charge in here, what I'll omit, but let's, okay, sorry. Let's see if the eraser works. So, all right, integral over the surface of A of B. Well, at least this is, you know, this is our guess, right? And this is a group element of H because, well, we're exponentiating by a Lie algebra element of H. So far so good. And all the things have to be preserved, all these properties, so horizontal composition, vertical composition, and so on. And if you want to, and this is not so easy to do, but you can sit down and actually check that these functors, you know, what it means for this map to satisfy, you know, all these rules. But basically, if we want to just hand-wavily think about it in an intuitive way, we can say, so we had learned that G goes to G prime, which was equal to the target of one of these identity two morphisms that start at the identity times G, right? So if this is, you know, if this is G, so we have, if you want, here we have a path-ordered integral of E to the integrated over a path gamma prime, which is not gamma, right? Now I want to basically, I go from a path gamma to a path gamma prime between the same 2 points with this surface sigma. And I'm saying that gamma, and these have by the func, you know, by f, they have to map, you know, each of these things has to map to its corresponding thing in the category. So here I have G prime will have to be equal to the target of something of the shape of this shape times the usual old holonomy, right? So far so good. Now, if we know that the original functor between categories has to preserve all the product structures, right? So we can take these two together, and now the signs, okay, the signs are sloppy, but believe me that it will work out. So I think it should be, on the one side we have this, and on the other side we would have integral, and here we compose gamma with gamma prime inverted, right? Because we're taking, you know, one of these to the other side of A. So that means that A is now being integrated around a closed thing, right? Because we're going along gamma and then along gamma prime minus 1. Here both go this way, and here we go one direction and back down again, right? Describing a closed loop, which, if those loops are small enough, Stokes' theorem tells us that this should be e to the integral of the f of A over the surface, right? And where f of A is equal dA plus a half A wedge A. And this should be true, right? I mean, here it's true for small enough little loops, but in fact it can be shown, because everything is so smooth and we're only considering smooth functors that preserve everything. It can be shown rigorously that this is actually true, and this implies that the T of B, because we can take this T up into we can differentiate this T up into the algebra, so this would be, T underline of B is has to be equal to FA. And this, I'll go to the next page. This is basically what we call the fake curvature, which I write curly F, fake curvature, which is equal to, let's say, FA minus the T of B. And this has to be 0 for well-defined higher holonomy. I'll just write it like that, you know what I mean. And this is called the vanishing fake curvature condition. And this is somehow, okay, the vanishing of these higher fake curvatures is kind of the guiding principle of underlying all these gauge theories. And indeed, if you take some traditional gauge theories, both the super symmetric ones as normal old-fashioned ones like BF and so on, you will find that in many cases, and I have examples, and if you take any of the papers with my name in it, there will be examples of known gauge theories, completely normal ones, not higher in any sense, but whose equation of motion can be rewritten in terms of the vanishing of a fake curvature, which will be constructed just, you know, out of the ingredients that the theory has, because even any normal gauge theory can always be put into the higher setting, into the categorical setting, right? So there is a way to express most of the equations of motion that we know and love in these terms.
What do you mean there by well-defined higher holonomy?
This drawing with the fact that I can transport a path along a surface in any way, and I will get the same result. It's like, yeah, like holonomy, really well defined, but higher, one step up. Here we're still always doing just the two-dimensional case, and we're not that much higher, but okay. So this is a guide. This is an important constant. There's a guiding principle that will accompany us, and also the fact that now there is this curvature, this fake curvature, which is made out of not just A but also B. B contributes to this thing. And in fact, now of course, a fair question is to say, well, does B not have its own curvature? Like here we have FA. Does B not have a curvature? And yeah, in fact it does. And I just write it Z here for lack of actually, I could call it H. Sorry, why don't I call it as we do in physics? And I could call it H, and that's the curvature of B. And it is a three-form curvature because B is a two-form. And this will be equal to, what would it be equal to dB plus the action differential of A on B, right? Which kind of makes sense, right? That they would mix in this way. I mean, let's say it makes sense that also the curvature of B would be affected by A, and there's not many ways in which A can affect B and give a three form except for this one that I've written down. So why not? There's no better reason for this to be called the curvature of B. Well, there is, and we'll see it later on, but for now this is just the best reason. And then you can also write down actually finite gauge transformations for this. So you can say that A goes into A prime, and this will be the usual, but with change. And so here we will have the T of some A, where the gauge parameters are now a small g, which is a g-valued function, as usual, the one you know. And then there will be an A, which is now a one form on the algebra of H. We've doubled everything, right? We've doubled the spaces, the categories, the functors. We have an A and a B, where we also need two gauge parameters. There's no way around it. And of course, always you start to notice also something else recurring, that there's always a degree difference between object 1 and object 2. So A is a 1 form, B is a 2 form, paths, surfaces, function 1 form, etc. Right? And B can also be checked to transform, and this will be alpha of G on B plus, now I have to check. Because this I always get wrong, alpha of A prime on A, and then a kind of a curvature for A, which makes sense, you know. It's kind of like A would do. So okay, why are these the gauge transformations? We'll see that later on, but for now, hopefully I can get to the point where I show you how to derive these in general. But for now, as an exercise, you could try to see that under these changes, when f, the fake curvature, goes to the fake curvature f prime, so, you know, keep in mind the fake curvature is the whole thing here, that f prime is still equal to 0. So that the vanishing fake curvature condition is preserved under gauge transformation. And if you really try to go by trial and error and find the most general transformations that would protect this condition, you would end up with the same. I mean, this is, so right now this is our best, let's say, trial and error argument for this being the actual gauge transformations. Later we get more rigorous in how these come about. So yeah, so much for that. Okay, we have said that we can differentiate the two group, and we have said that now, okay, so the differential, all of this lives, of course, in the differential cross module. Actually, I just call it lead to algebra because that's what we're going to call it. But just to be aware that this is not a new structure in mathematics, this is something that has existed for a long time. Lead to algebra. And the strict here really refers to the fact that G and H are Lie algebras. So this was, we said, made out of G, H, T, and alpha. And we had A that lived in G, B that lived in H. And we have these conditions that still come from the categorical arguments from before. So we have these two rules that have I written them down? Yeah. These ones. So the differential version of the other two conditions, right? So that's the kind of structure that A and B live in. That's how they interact with each other. That's what they have to, you know. So that's how their algebras, let's say, interact with each other. So far so good. But as we have been discussing since the other day, at the end of the day, these structures that I've shown so far. So again, you know, BF theory is an example of this, because if you look at BF theory, you look at the equations of motion, you get P equals F equals 0. That satisfies a fake curvature condition, right? And if you put BF plus B wedge P, that also satisfies the condition, and the T map will be an identity map or something. So you will find many theories that already satisfy this condition on their own, that were just written down for different reasons. So spin foam models, apparently, I know nothing about it, but apparently they are based on representations of these D2 algebras. Now, of course, representation theory for these objects in general is not at all understood, but for what is understood seems to point towards spin foam models really being, in some sense, I guess they hope the quantum version of whatever topological gravity you can describe with the B wedge F and BB theory. So that's all stuff that, you know, let's say hyped this area of research because it was, you know, promising for the quantum gravity discussion. But the thing is, all these theories I've cited actually, and we have discussed ABJM and, well, we discussed, you know, I've claimed that ABJM and BLG theory and so on are also just examples of these theories based on these strict two algebras. And again, in my notes I have the reference to the two papers, one that proves the BLG and one that proves the ABJM. They're both written by Christian Seemann and Sam Palmer, and they show how these relate. But basically, that just tells me that we still haven't said anything new, and we still haven't really solved any of the problems, because both of those models were ultimately not 100% successful as we would have liked. So what have we done? What have we achieved? Nothing. We've just rewritten everything in a very weird way. But this very weird way is much more generalizable than anything we've had before. So indeed, when the PLG structures, these triple brackets that they invented for these two brain models, when they came up with those, everything was tried to generalize these. So when they were living in some vector space with a metric, we tried to make the metric with indefinite signature. We tried to make the entries complex, real, Hermitian, non-Hermitian. You know, it went back and forth, but at the end of the day, you know, no generalization really held up. And the only interesting examples were always the you could say trivial ones that didn't give us not really as new physics as we would have liked. So there was nowhere to go from there. But from here, the generalization is, I hope pretty obvious. Well, no, it's not obvious, but I'll tell you what it is. So we start now. We'll just focus on the algebras. Forget about the groups. Forget about the categories. I'll just go from the Lie2 algebra. I would like to generalize this. Generalize. And I will generalize it. I will just say I will map these things to so actually, well, I will take this to something that I will call WV. I'll explain in a minute. mu1 and mu2 of W. Whereby I mean here these two are just vector spaces for now, linear vector spaces. mu1 is a map that goes from V to W, just like T used to map us from H to G, remember? And mu2 is something that takes at least one of its ingredients will be a W. It'll take a W and something else to whatever the something else. So I guess, sorry, this is written stupidly. I'll call it the something else. I'll just call it X. And this will take W cross X into X, where X can be both either W or V accordingly. And basically the difference is that this V and this W here are not just vector spaces. I'm not saying that they have a Lie structure. I'm saying that that these two products exist. I mean products. So this is actually just a map, but it's a one product if you want. So we have a one product and a two product at least on these two vector spaces that just map from one to the other in this way. And I'm not saying that there's any kind of property like any sort of Jacobi identity on a product on two W's. So for instance, mu2 can take W1, W2, and it will give us some other W. Or it can take W1 and V and give us some new V, for instance. So, but I'm not saying that this mu2 is basically a two product, right? It's like a bracket. It takes two entries and gives out one. The mu1 takes one entry, gives out one. And I'm not saying that I'm not giving this any properties, this mu2. I'm not saying it satisfies the Jacobi identity or even that it's antisymmetric, but I will, from now on, I will require it's antisymmetric just to have some sort of stability. And if you remember the relations between these guys, we have this thing that said that the action of G, sorry, the action, notation. The action of X on Y, the target of that, was equal to the bracket we had said of X with T of Y, right? And I had said this was the bracket in G. Now we don't have a Lie bracket in G, but we do have a mu2 between W and mu1 of V, because the mu1 is basically a little bit like T used to be. So here I've just rewritten this in my new notation, and on this side I have mu1, and the action of x on y, so the action of something in G on H, is given now by this, in particular by this, the action of W on V. So here I have mu2 with mu1 W on V. Just abstractly, I'm just rewriting the same stuff from before in this way, and I write mu2 because I don't want to give the impression it's a Lie bracket, because it's not.
So the only thing that you are relaxing with this generalization is that there is no, the Jacobi identity may not be satisfied?
Yes, you can choose. You can actually, in fact, you can relax either the Jacobi identity or the antisymmetry of the product. Either way, they're completely equivalent. Much like in generalized, for Courant bracket, Courant algebraic structures, you know, you can choose the Dorfman bracket to be antisymmetric. Well, one of them is antisymmetric and doesn't satisfy Jacobi. It doesn't satisfy Jacobi. The other one satisfies Jacobi, but is not antisymmetric. The two choices are equivalent here, the same. I always choose the one where the brackets are antisymmetric, and the Jacobi iator is not zero. Convention, more commonly used in the literature, let's say.
So antisymmetric, but not Jacobi is not zero.
Not Jacobi, yeah. So you have two, in principle there exist two functors. There exists an associator and a Jacobiator, and one of the two is trivial. You have to choose which one. But there is categorically, the two things are completely equivalent.
But the path is still bilinear?
Yes, the bracket is bilinear. It's yeah, and it is. And we will see in a minute. I mean, I haven't told you everything about it yet. I'm basically trying to say what can I do to generalize. Like really naively, I want to generalize. I'm going to relax some stuff. Let's see what happens, and I will give you the complete answer, correct answer, nowish actually. So far, well, this is just to show you really where things have come from, right? Here, the important thing here is that we already know how mu1 and mu2 have to mix. And we know that from the categorical arguments from before, right? Now, you remember the other categorical thing I knew here, there was something with a bracket y prime on H. Now, I don't have a bracket on H, so I'm not going to say anything about that for now. We'll see how, we'll see what develops. But I don't, in principle, I've only created this kind of object, so I can't put two V's in here so far. So indeed, the answer happens to be, because this is a generalization out to semi-strict case, but in general, of course, you can also ask, we've only talked about surfaces, you can easily ask what happens for volumes. It's not only strings that exist, there exist branes and, higher, or even if you want to quantize just spacetimes, different spacetimes, they can be of higher, they are of higher dimensions generally. So to generalize also to higher dimensions, not just to relax the strictness, the answer is going to be, well, I'm going to make a big claim that is not completely true. But it is basically, I will tell you why. So the answer is that is this structure called an L-infinity algebra, which is also called strong.
Sorry, the answer to what question?
To how to generalize this to arbitrary dimensions. Let's say just arbitrary dimensions for now, not to, because as you go higher up, the strictness gets lost anyway. Once you're at 3, you can't have this two-group structure anymore anyway. Although I still don't know what the 3 cross modules are, so maybe that's so strong homotopy algebra is also the name. You recognize the words, the homotopy, and the strong, I don't know where that comes from, but okay, that's the name. And the definition of this, what is this? It is a vector space complex, I forgot again something, the graded vector space complex. So it will be, I write it L equals the sum over I of Li, where every component's degree will be that I in the index here, and together with, endowed with, K-ary, multilinear, antisymmetric, brackets, or products, let's write products mu k, that are graded as well and have degree 2 minus k, again convention, my convention is this, depends, have degree 2 minus k and satisfy, with these products such that, I mean, I wouldn't take anything written on these slides too seriously, neither grammatically nor mathematically, but okay, such that, and we have this condition, write it out once, we will not need it as such again, but just so you've seen it, this is a sum with a cosine sign, which luckily Jose has already explained, so I don't need to go into that. And that depends on the permutation. These are sigmas are permutations of indices. These are actually unshuffles, but don't worry, we're not going to worry about too much now about the details. So this is mu j plus 1 acting on mu I of L sigma 1. L sigma sigma I, well, L sigma I plus 1 all the way to L sigma j equals 0. And these are called higher, or at least these are called, I call them higher Jacobi identities. Of course, since everything here is graded, these have to be satisfied degree by degree, and you can see what is going on here. I am mixing products of one degree with products of another degree. We'll write it out now for the case n equals 2, but in any case, this sum can go in principle up to whatever, infinity, that's why L infinity algebras, but we will always consider finitely truncated ones, so that's what we call a Lie, and this is where the falsehood comes in. A Lie algebra we will call, and this is a truncated L infinity algebra with all the brackets with k bigger than n plus 1 equal to 0. Now, the Lie algebra, why do I say this is a bit dodgy? Because this term, Lie algebra, comes, strictly speaking, from the category theory picture. So from, taking really higher categories, so we've talked about 2 categories, but this goes up 3, 4, and so on, all the way to n. You can imagine that these relationships and these Pfeiffer identities and so on become more and more intricate, more and more complicated. So we already had 2 types of composition. With 3 we'll have 3, and then we'll have 4, and they all have to mix, and they all have to be well defined, and you can imagine this becomes a horror show. And so the claim is that these L infinity algebras, which already existed in the literature, so they existed both from string field theory, from higher string theory, they have been, the ghost going through mathematics, not through Europe, for a long time. But basically, so they have existed and they're well understood, and they're well studied, and people know how to manage and deal with them. And because the n equals 2 correspondence can be proven rigorously, and I will have references for that in the notes, the higher than 2 case is not, as far as I know, yet proven rigorously. It's just everything looks like it should be the correct structure. So this definition that I've written here does not come from category theory. This comes from before, and we just hope. Well, people much better than me and much more rigorous and much more mathematicians than me are completely convinced that this is true. It's just that I don't like to say things that I don't know. So I guess in principle you can take it for, if the gods think it's true, what does it matter if it's not true?
So that's just dual to that is the fact that you have a VGA, right? So it's
exactly.
B squared equals 0, and Z has always
we're going to get to this now, because that's the way to look at, to do physics. That's much easier way.
So then the way you wrote these permutations, I suppose they're such that the first I guys are ordered, and then similarly the other ones.
Yeah, these are sorry, these are not exactly permutations. Actually, these are unshuffles. Yeah, whatever you want. Yeah, unshuffles. So they're not just random permutations. They're permutations where you permute two sets that are ordered. So that maintain, you know, growing indices within each set. But that's not. Okay, you will see that described well in the notes. It's not going to now do anything to our discussion here. Yeah.
So, so the two-level has recently been very well known, quite well known.
Yeah.
And then, but if you're going up and up, do you think it's gonna just be a bit more complicated, and then be the same? As it's like other the 2 and 3 and 4, does it look like they're going to be this exceptional?
It's worse. I mean, it doesn't. Well, it doesn't look like it. A way to look at this whole story categorically is to go by simplicial sets. And when you look at them, it does not look like there's. At least that's. I don't know. I don't know the whole story.
Yes.
But let's say the first bit of the story that I read, it doesn't look to me like anything gets ever easier. This just gets worse and worse. I mean, at some point already at level 2 you start to need to use Mathematica to compute stuff. I mean, and it's going to get worse probably. I don't think there's any closed, nice, elegant way to deal with these things. And that's why also the proof for the high, like the making the categorical relationship higher, rigorous is very hard. Yeah.
Sorry. I was just going to say, so the fact that you have so many products and you have to have all of these interrelationships between them isn't enough, because it gets more difficult in other aspects.
Well, it depends what do you want to, what becomes more difficult, right? What's the question? What do you want to do? So, to do physics, you know, I mean, mathematically, what would be lovely to know about these things? Some sort of representation theory, right? I will show you now an example, but that's really the only thing I have to make any of this concrete in any way. I've written mu k. Mu k means nothing. Before we had actual deep brackets, we had things. I don't know what mu k. The only thing I can tell you about mu k is it's antisymmetric. It's multilinear, you know, and it satisfies this equation. It's just a notion, right? Yeah.
So in the strict case, when n equals 2, you could essentially, the structure you got, you could essentially rewrite it, or at least describe it in the language of the algebra. And what about n equals 3?
And already I thought about, I mean, in principle, well, at every step you have the highest Jacobi identity is satisfied, right? So at level 3, if you had a 3 group, unfortunately I don't know enough about it, but I think you would have unsatisfied 2 brackets, but the 3 brackets would satisfy this fundamental identity from the Filippov algebras. So basically where you fix all the entries but the last one, and you let it act on, you know, the last slot is empty because that's how it acts in an adjoint way on any other elements of that same vector or of the same vector space. And then that would act as a derivation, so that would have a higher identity. But the lower ones you would already lose them again, I guess. Mm-hmm. So because you know, okay, we'll see. I'll show you now. So if let's take this very abstract notion here, and let's just write it out for n equals for the n equals 2 algebra. So we're basically saying that mu3 is 0. So if we read this carefully and we do it, we will find that we have two vector spaces. L will be given by an L minus 1. I choose the grading now. I'm choosing negative to 0 grading. It's just convention in the literature, and we could go 0 and 1, whatever, but I choose it like this. So these are our two vector spaces. I call them in general V and W. Again, in all my papers, our papers, this is the nomenclature, so might as well use it. And here what do we get? Well, because of the grading, because this is degree minus 1 and this is degree 0, you can already see that in mu2 has what degree? 0, right? I said that the k's have this is their degree. Mu2 has degree 0, so mu2 with two v's, both of them minus 1, what can it be? Nothing, right? There's no degree minus 2 space they can map to. Mu1 after mu1 on v, the equation tells us if you put j equals 0, I equal 1, that this is 0, right? On the other hand, also mu1 or w, simply by grading arguments, there's nowhere after w, there's nowhere to go, is also 0. again, grading arguments, mu3, what degree does mu3 have? Well, 2 minus k, it has degree minus 1. If I put anything further of degree minus 1 in here, no matter what I put in the other two slots, it's going to be 0,
You said
right?
mu3 was 0. mu3 is 0.
Sorry. I did it wrong. Ah, I shifted all the names, sorry. That's my, yeah, okay, I'm an idiot. This is the condition, this was correct. And what I wrote before, what I wrote here is
Okay,
from
greater than
mu4
3, sorry.
greater than 3. Yeah, sorry,
No, it's all right.
I always do this. And I will do this again. So, so just try to remind me that I'm, because then I have a p, which is n plus 1, and you don't want to know what will happen with that. So anyway, that's, yeah. So, mu3, because it has degree minus 1, acting on v will, v with anything will have to be 0. So mu3 can only exist with 3 w's. And how does it come up out of this equation? Well, if you know, it's worth doing this as an exercise if you want later on. Put j equals to 0, I equals to 3, and you will see that mu1, mu3 of w1, w2, w3 is equal to mu2 of w1 on mu2, w2, w3 plus cyclic in 1, 2, 3. Of course, you know what I mean, right? This is the Jacobi identity for this structure mu2, and this is evidently not, this is not 0, but it is equal to the mu1 of something, meaning it is something that is, that's why they are called homotopy algebras as well, because this mu1 is a map such that mu1 after mu1 is 0. So in some sense we are violating Jacobi, but only in a controlled way, only up to a mu1. So if from here we were daring enough to go back to the category picture, and we remember what was mu1? mu1 was the map from G to H. mu1 was, from H to G, and what is the Jacobi identity? The W's would have been elements in G in the old in what we did before, right? So in the Lie algebra of the gauge group G, what does the Jacobi identity say on a Lie algebra for the Lie group G? It says that that group has an associative product, right? That the normal group product is associative. So by saying that the Jacobi identity is not true anymore, we're saying it's not associative anymore, but it's not just crazy. It's not associative up to a t, up to one of those two more, you know, well, yeah. In a t-controlled way, let's say, we have broken stuff. So we're kind of, in physics language, you could say up to something exact, right? And just like in physics, exact things are not so dramatic, well, depending on who you ask. Here, it's definitely not 0, but it's not the end of the world either. We can still play around with this. We still have some, because as soon as we act on all this with another mu1, that stuff, that's gone, right? That term is gone. And again, okay, you can of course here also invert and have mu3 on the mu1 of v with a w1 and a w2, because the two bracket, as we had written down before, the two bracket can also mix v's and w's. So this would just be if v was acting on the w's. Sorry, this is what. Anyway, there's not so much to be read out of this. It's just a fact, and then you will get another fact. Will be something that will mix. You can then also mix mu3 and mu2, of course, you know, with all the permutations, and it will be mu2 after mu3 with all its permutations. I'm not writing it out because it's very long, it's like a paragraph, but you will get all these relations. And there's not, I mean, and here actually, sorry, I won't put a plus, an equals, I'll just put a minus here and say mu3 after mu2, because this could, of course, in principle be equal to the mu1 of some mu4, right? But we don't have a mu4, so that's where we stop, and that's where we are back to what we know, to something that, well, has a higher Jacobi identity indeed. So, to the question of mu3, of going back, let's say, for fun, to mu3 equals 0, what are we left? Sorry, I didn't write down the easiest. Did I write? I didn't write down the easiest things up here. So you can also read off that mu2 or mu1 of v on w. So this also follows from the definition. Is mu1 of the mu2 of v with w, right? For instance. So what's left when we set mu3 to 0? Well, this equation goes away. Here we end up, here we end up with two types of Jacobi. I mean, these change to actual, this goes away, these become actual Jacobi identities. And indeed, what do we end up with? Well, we end up with W, which has a mu2, which is V, right? Because it now does satisfy the Jacobi identity, so it can be rewritten as a Lie bracket. So W basically becomes a G. And in the same way, of course, we can easily construct a product between two V's, V1, mu1 of V2. And if we go back to our old language with this is like saying, sorry, I should have written it the other way around, just to make contact with our previous type of writing. So this is this is the action of the T of V1 on V2, and if you check the previous stuff we had written down, that was going to be V1 on V2 on H, which is now V, which, since all the Jacobi things are satisfied, can be seen as a H. So we get back, so this is a true generalization of what we had before, and we can easily go back by setting our Jacobiators at the mu3 up to 0. So this is the kind of general structure we're interested in, and this for any n in principle. Of course, calculations can really be done by hand only for low numbers, and actually already at level 3, I mean, there's not much done. It's just too painful. But we've done some stuff at n equals 2, and when I mean some stuff, I mean a little bit of physics in inverted commas. If topological field theories can be referred to as physics, but okay. So actually, that's what we're gonna, I think, get into, unless I've forgotten my plan. No, I think we're doing pretty good. So okay, so far, well, basically what we want to remember is that there exists this big fat equation that tells us how to mix these different brackets. They're all graded. The vector spaces underlying them are all graded, and that's a structure we believe we will have to base our higher gauge theory on, because we claim that this solves the higher holonomy problem. So let's look at an example, a concrete example of one of these structures in nature, I will say. Yeah.
In the notes, you say that it's a semi-strict.
Yeah, sorry. Yeah, semi-strict now. Yeah, okay. So I've read. Very good. These are all going to be semi-strict higher. All these higher algebras are going to be semi-strict, or even at the level 2 when we have the mu3 not equal to 0. That's semi-strict because, as I said, strict is when G and H are Lie. Now I'm going to V plus W, not strict anymore, semi-strict. If I had chosen the Jacobiator to be 0 and the antisymmetry to be broken, that's what they refer to in the literature as hemistrict, in case you come across it. But the two things are really equivalent, so whichever you prefer. In any case, not strict anymore. So an example could be the what I would call here the n-plectic manifolds, which are a higher version, a categorification, if you want, of symplectic manifolds, and I will call them M with omega. So this is a smooth manifold M with a n-plectic n plus 1 we'll see, form omega such that omega is closed and it is, guess what, non-degenerate. This is our definition of non-degenerate. So this looks already very much like a symplectic structure, right? That Jose told you about in the first day. So something closed and non-degenerate, which therefore will just play the same game as in symplectic geometry, as we do as as physicists in symplectic geometry, what's of interest to us, and we can define ourselves Hamiltonian vectors and forms vectors corresponding to n minus 1 forms alpha, and we'll define them via this equation that d of alpha is equal to minus convention ix alpha of omega, where this I indicates the contraction, which means this, right? That's you've been to the courses, you know what this means. So let's check. This is an n minus 1 form, right? This is a differential is 1. This thing here is supposed to be n plus 1. The contraction is minus 1, and I think I'm even okay with the gradient. I mean, this makes sense, right? I think. So again, just like in you know, when let's say Hamiltonian mechanics, or when or quantum mechanics, if you want. I mean, just the usual definitions. Hamiltonian vectors, only that now they're not associated to observables that are functions, but to forms, n minus 1 forms in this case. I mean, n minus 1 forms for an n plus 1 structure, and then given this, I can extend this. I can also define. Who's to forbid me? Well, I can. Okay, hang on. Before I define anything, let's see who we're dealing with. So, consider first of all if a graded vector space complex, an L that I will call L the function of functions on M. Here I will have a little map that sends us to the 1 forms on M, and then to the 2 forms on M, etc., all the way to the n minus 1 forms on M, and I will put a little hand here to say to the we'll end on the Hamiltonian n minus 1 forms up here, because they're not all n minus 1 forms on a d-dimensional manifold will have such a Hamiltonian vector, so we'll just take those. And we have this. Sorry, this is pi 1. This is pi 1. This is pi 1. I'm calling them pi now just to say it's an example of an L infinity structure. I could call them mu like before, but because this is supposed to be my classical thing, I will call them pi to remind us of Poisson in a very optimistic way. So, and I will then define, so the pi 1 on some function, I will say is the d of that function. And I will say that the pi k, this is just another k-ary multilinear antisymmetric product, and I will say that pi k on alpha 1 all the way to alpha k will be equal to some sign, which I'm not going to get into, and then the contraction of omega with all these Hamiltonian vectors associated with these guys, where alpha I are Hamiltonian n minus 1 forms on M. You can see that there's only so many times I can contract, so there's, according to what n is, there is a natural end to the products I can take, right? Anything after certain n will be 0, and in particular after n plus 1, right? Because after that, omega is gone. There's nothing else to contract. And you can also see from here, actually it's already worth mentioning here, that anything, if alpha is exact, the corresponding vector is obviously 0, right?
I'm a bit confused. All your maps are called pi 1, but then you...
Yeah, these are, no, between, it's like D, it's like a difference, it's like the differential.
Oh, right.
It is, sorry, because it is indeed D. On F it's D.
Okay.
And then of course
These pi k are different things than your...
this is basically a specific example of mu k, let's say. And I call them pi because I want to allude to Poisson, to some sort of classical mechanics for p forms. That's why I said example in nature with inverted commas. And by nature I mean mathematics. But I mean it's something easy to see. I mean it's something where you can see that the structure is not so insane. I mean it's not so. Well, it is, but this is an example where you can see a very simple example. Now, of course, I could have here pi k, or even pi k, any k of beta, where beta is some smaller than p smaller than n minus 1 form on M, beta with alpha 1, alpha k minus 1, all of these I set to 0. Just because, well, I don't have to actually. I can invent myself products, other products with lower forms that satisfy all the L infinity conditions. But without them, it's simpler, it's easier, and it can be shown that actually, even if I do define myself, so for instance, I could have a pi 2 between alpha and f, which could be, this has to map to functions, right? Because the grading, again, is the same. Here I want the same grading as before, so I'm taking a one form in a function and I want to map this to a function. So how can I do that? Well, I could do it with, like that, for instance. And I think, if I remember right, this even satisfies, this would even satisfy the two algebra relations, but you can show that this is just a two algebra is homomorphic to the one where this is 0. So why complicate life? The only time it's interesting to complicate life in this way is when you want to relate things to other known structures, or when you want to use these things to have some non-commutative structure on a space where you want to do field theory, and then you can you can say that in this sense alpha acts as a derivation on f and some But anyway, for now, for us, it's of no interest because it just complicates matters. And this thing was first written down by Chris Rogers, one of Baez's students. And yeah, we thought we could improve on it, and we did all these other complicated mixed products, but turns out that everything is just the same, really just homomorphic, so the same, so not interesting. So anyway, at least that's an example of something. And if you and I would recommend again, as an exercise, to just do this yourself. So take a three-dimensional manifold. So take M to be equal to just R3, the easiest, and say omega three-dimensional manifolds. The volume form is always a two-plectic structure, right? Two-plectic means it's a 2 plus 1 form, a 3 form, non-degenerate and closed. Well, the volume form presents itself. Indeed, it's the only one you can take. I mean, it's the only one there is. So you could take this, and then you could say, choose a basis for vector fields, xi equal d on d xi, and I should have called these ones x1, x2, x3, so not confusing. So this will just be the derivatives along xi, and you will find, you can do this little calculation in your head even, that they have corresponding one forms, Hamiltonian one forms, psi I equal to epsilon I j k x j dx k. Anyone who does this, a lot of this, finished? Okay. This is good. This is pretty good. So I just want to say, take these. Okay, do this as an exercise. Take these and figure out what is mu2 of psi I psi j and mu3 of psi I, psi j, psi k. Write it down. See if it reminds you of anything, and and then deduce why I call this the Heisenberg N algebra. That's enough clues, I think. So anyway, no, but sorry, these I call them mu again. They're still pi's. I'm sorry, I only did pi. Of course, the d of an f will be, just the d. Sorry, wrong side. Pi 1 of f remains this, on R3 now, and well, this is a very quick calculation. Actually, as an exercise in the notes, I think I said do it with S3. Calculate the pi 2 and pi 3 on S3, and get yourself a nice little new fuzzy sphere. But anyway, this is a way to see. So yeah, the point is, I'm trying to mimic classical mechanics. I'm trying to say that there's some sort of algebra for observables, which now are also P forms, and that in principle, if one was so inclined, one could want to quantize this pi structure, and this whole thing, I call it big pi n, as in the Poisson algebra of these local observables, which is wrong because it's not Poisson, because what's missing here in all of this is an associative product between the one forms and the function that is preserved by these products. So it's not exactly Poisson, but you can see why I would call it that, and why I would want to quantize these things into mu-k structures and argue that this is how I quantize higher dimensional spaces. Later we'll do physical models. I don't know why I keep using these words, but I don't know what else to call them. Chern-Simonsy models.
So let's have a 10-minute break.
It's pretty. I managed to get it. Faster than the other.
How's it going?
I mean, I say that I managed. The next thing will be more. I will not write down many equations. I will write down facts. I guess it will be better. But it's understandable more or less.